All right, so today we are going over new chapter, motion in one direction, or one dimension, sorry. We have, all introduced some tools with vectors last time, and you've, introduced some tools. Now it's time to see how those can start to play in actually using them in physics. So let me actually get this set up. Okay. So motion in one dimension, think of it just like a number line, things just moving left to right or up and down. We can begin by looking at how things move. This is what is known as kinematics. It's a pretty much a large branch of mechanics. All things that move are in this section. Why kinematics is important is because it will allow us to, not just observe and write down, how things move. We can then predict things that we might not even have measured before. We'll get to a bit of that later. I don't think today. Okay, so in kinematics, it's movement. It's anything that's moving. We start out in one dimension. We want to make things simple. So we're going to think of all of the things we're going to be giving as an example and reducing them down to a single particle or, a single point. There's the example in the book that says something like a race. In a race from start to finish line, the only important part is the very front of, I think it's a horse race, so the nose of the horse. So that's the only point that is being measured from the start to the stop. That's what you can think about the motion of this, large complex object. Maybe you'll have many, individual complex parts. What we can do is just reduce it down to a single point that's moving. That's easy to track. Okay, so we have, I made a little example of a car, and we're going to be looking at I think last week, or I think yesterday, I talked about the example of going to the grocery store, and you might take this big, long, complex path, and you have this large distance, but maybe your displacement is different. So what I'm trying to show with this car right here is, first off, the car has many complex parts, but I'm going to reduce it to, I'm just going to measure distances around this point that I put in the middle. And this is the same car. This is just two separate pictures of the car. So I took a picture at one instance and then took a picture at another instance and saw that the car changed its position. So I'm going to measure everything around that point in the car. At this first instance, the car is, by the way, the car is moving this way. So I'm going to measure around this point. So I'm going to say on this number line, to the right is going to be a positive direction, so positive x as you move to the right. It's typical convention to have things that are moving to the right are positive, things that are moving to the left are negative. We're going to measure this position as x sub I. Okay, and then an instant later, we take one picture, then we take another picture of the car. We're measuring around the same exact point to make it simple for us. And that is what we're going to call x final. Now the difference of these two positions is called, you can say difference in position or change in position. That is also a good place to call, or a good thing to call, displacement. Placement. That. And I believe this is what I wrote last time. The difference in position from one point to another. From one point to another. To another. Okay, so this sort of change in position, we could also measure, we could also label this as its own sort of range of its own distance. We will be calling it delta x. So that's just this Greek symbol out front. It is just a triangle. That just means change in position. So delta x is equal to the final position minus the initial position. So it's always going to be final minus initial. My colors went away. Go like that. Right there. Okay. Now we have this way to measure, changes. Also, oftentimes we want to know an object's speed. I made it too big. There, let me move this up here for right now. Okay, oftentimes we want to know an object's average speed. Something you know about speed is that it's different than velocity. Speed is sort of just a positive value. Speed is just measuring how much distance you go and how long it takes you to do that distance or cover that distance. So we'll say average speed is total distance over total time. And I believe the symbols, or the symbol for distance, I don't know why, but it is an S. So distance over, so total distance over total time. And I'm actually going to put it as delta T. So just the change in time. But speed isn't always what we want. Sometimes we want something more accurate, like velocity. Velocity is going to give us, the rate of change. It's going to tell us how quickly something's moving position, but it's also going to tell us the direction. So it's going to give us more information. It's more useful. I'm sorry, let me do this again. Keep hitting the button when I'm not meaning to. There we go. So average velocity is, we could write it like this. So just v, and it's going to be sub. So I'm just going to try to spell, or abbreviate average, and specifically in the x direction. So the average velocity in the x direction is delta x, so change in position over delta t. And I could write that out in full as x final minus x initial over t final minus t initial. And the last thing we can sort of notice about this is if we look at the first part, this first section, I can get delta x by itself by multiplying delta t over, multiply both sides by delta t, and I could notice, I'll just say we notice that delta x, so the change in position, is equal to the average velocity times delta t. So it's just sort of me rearranging that equation to make something useful. Maybe I can use this later. Maybe I'm given a problem with velocity and time, and they want to know how much ground I cover, or how much distance has been covered. Okay, so we're on our way to actually measuring things that are moving. We're going to be doing an example up next, and let me pull it up. Okay, so we're going to be doing this example, average speed and average velocity. So the problem is, let me zoom in a bit. You're playing fetch with a dog, and the dog is initially standing by your feet. We can mark this distance as 0. Then the dog jogs 20 feet away from you in 1 second to retrieve the stick. Then it paces back 15 feet towards you in 1.5 seconds. This is where the dog stops and begins chewing on the stick. So we have this path that the dog takes. It goes, one direction and then back. So let's, a way I like to always keep things clear is by drawing a picture. So I drew a quick picture, or actually I need to show you the question. What is the dog's average speed and average velocity for the total trip? And I drew a little picture to get us started. What we have to do is, or the way I like to start is by drawing a picture to make everything clear for me. I'm going to make this sort of scale in front of it, in front of the dog. So right where it's standing, right when it begins, that is 0 feet. And what's the maximum distance it goes? So it jogs out 20 feet. So it jogs out 20 feet. And let me quickly just make some markings on here. Half of that's 10. Half of that is 15. And half of that is 5. All right, so now let's actually, I'm trying to keep the values in frame. Okay, so now let's draw the path of the dog. So it starts here. I'm just going to make a little line. Say it starts here and it goes 20 feet to fetch the stick. So it goes out this way. 20 feet. We'll call the place it starts, we will call that x sub I. And we will call this position out here, we'll call that just x sub. So let me, clarify that it doesn't quite matter what the indices are unless it just has to make sense for you. So this is not where it stops, completely the end of the problem. It's just sort of an intermediate step. So it goes from here to here. So at x sub I, that is 0 feet. At x sub 1, that is 20 feet. It then goes from x sub 1 and it's still in frame. Actually, before I do the next step, I want to say that we should also mark down the times that it's taking to do this trip. So usually right when we start this problem, or right when we begin, we can also label the time. So we'll say this right when we begin keeping track, we will call that t sub I. So that's just holding a timer. And right at the very instant we hit the timer, we say go. That is considered 0. So that's the initial time of 0 seconds, right when we start. Then right when the dog gets all the way over here to position 1, we looked at the watch and we saw that it took 1 second to go all the way over here. So we'll say t sub 1 equals 1 second. Okay, now I will do the next step. So it goes from position 1 out here and it travels back towards you 15 feet. So that means it goes back 5, 10, 15 to right here. That's good. So it went from position 1, which is still out at 20 feet. And since I'm sort of breaking this, total path into sections, let's call this one this time. Let's call that, we're starting a new lap. On a lot of stopwatches, there's a lap button, so it restarts the counter. So let's say right here, I restart the counter. I call that 0 seconds again. And then we saw that it takes the dog it travels back 15 feet over here. So now we're at 5 feet. X feet. And this is the T final equals 1.5 seconds. All right. So we have all these values that we're given, and we can just sort of place them in the equations that I've listed before. Let me write out just average speed. That's one thing we want to find. Average speed. The equation for this was total distance over change in time. Okay, well, what's the total distance? So it initially, in the first pass, traveled 20 feet. And then it traveled back 15 feet. 15 feet. So the total distance is 35 feet. Total time is this is actually delta t, which is change in time, but it's pretty much the same thing. We'll say, I forgot to give this t sub 1 over here. I'm sorry, we'll just, let's see, t sub 1 minus t sub I plus t sub f. It's getting real small, t sub f minus t sub 1. All right, well, we will say this one right here is actually 2. That'll make it clear. T sub 2. Because that's where I hit the lap on the timer. All right. Okay, so pretty much that just means that this is getting hard because it's real small to write. Okay, 1.0 seconds minus 0 seconds. There we go. Plus 1.5 minus 0. And that's just a long-winded way of me just saying the total time is 2.5 seconds. Okay. Let me shrink this. Or at least move it up. Shrink it a bit. I'll put it right there. So we have total distance, total time. So I'll say average speed is 35 over 2.5, 35 feet, 5 seconds. That ends up being 14 feet per second. Okay, moving on to average velocity. That is VAV in just the x direction is delta x over delta t. I'm just going to put it over here. Delta x is, I don't need to do the intermediate steps. I'm just going to say final minus initial. And that's sort of the interesting thing about this displacement is it only cares about where it stops and where it starts. So it stops at 5 feet and it starts at 0 feet. So delta x equals 5 feet. Delta t, that is going to be the same as the first one, for the first part. So we have 2.5 seconds. Ultimately, we have the answer of the average is equal to 5 feet over 2.5 seconds. 2.0 feet per second. All right. So I'll writing quickly. You could tell when I have a lot of time to prepare my writing versus trying to write very quickly. Next up, let me go like that so you can see it before I change. Next up, we're going to maybe look at some other types of velocities. This is average velocity. You see, it's only taking, where I start and where I stop into consideration. But the dog in this example, it's moved to the right to begin with. That is a positive velocity. Let me very, boldly say this is a positive velocity when something moves to the right. When something moves to the left, that is a negative velocity. You see, when these two things are countering each other, and the dog ends up, very close to the place it starts, we have this small average velocity. But we've seen that the dog moved, a lot. It covered a lot of distance. How can we tell what the dog's speed was, or not, sorry, the dog's velocity somewhere else on its path? That's where we come into what is called instantaneous velocity. Let me go like that. Instantaneous velocity and speed. So this is, you could think of it as the dog example, or you could think of it as maybe a long road trip. And we have an average velocity, as the thing we've just done. We have an average velocity of 60 kilometers per hour. Now, this may be helpful if we only care about the average, but a lot of other times it's not useful. What if we want to know a specific speed we were going at a specific time? Since this is an average, it doesn't count for all of those in between bits. You could think of it like, well, on this road trip, maybe we stopped for a little bit, and maybe we went above 60 kilometers per hour at some time, just to sort of, make up for time. So it's fluctuating, but the average velocity doesn't give us that information. That's why we want the instantaneous velocity. It gives us the velocity at any specific instant. Okay, so instantaneous velocity is labeled as just v sub x. So I'll write this out. Still too big. About there. Okay. Instantaneous velocity is v sub x is the limit of delta x over delta t. So just like we've seen, that ratio we've seen before, as delta t approaches 0. So what does this mean? Well, let me write it out a bit more formally. So v sub x as a function of time is equal to the limit. This is t as it approaches 0. So this is what this statement above is referring to. You could think of it as the slope of the line tangent to the x versus t curve. The slope of the line tangent to the x versus t curve. What is that statement meaning? Well, I'll have another little picture example. Let me bring it up. So say we have this x versus t graph, and it shows this curve on this graph. So this is just saying what is something's position as time moves on. So as we start the timer at t sub 0, the object is at whatever we call 0, or whatever the origin is, these values. I didn't mark down any actual values on this. Then as time moves on, just another sliver of time, the position changes. So it is now up here. And it's a greater position. It's slowly moving away. Or it's moving with a positive distance. Then it gets to this point, and it starts coming back. It changes its direction. So it started moving the positive distance, and now it's moving back. That didn't quite match, but I think you see what I'm meaning. Okay, so we have this motion of whatever this is. It's going to be a lot of lines on here. I'm clearing things up. So we have this motion. What if we wanted to find, I don't know, the average velocity of something that moves with this motion? So we would take a picture when it starts, and we'd take a picture at the very end when it stops. And I believe that's this one. So we would take a picture when it's at this position, and then we would take a picture, try to be precise, we'd take a picture when it's at this position. You see, that's why I'm connecting these 2 points with this blue line. So this will be the slope. Try to write this clearly. Slope of the average velocity. Okay. But it goes from here to here. It misses a lot of the curve. There's a whole, area over here where we're not accounting for how fast this thing's moving. What if we wanted to find the speed? What if we wanted to find the velocity of this curve at point P right here? Let me get rid of these. That is where we need the instantaneous velocity that I have up here. So this is where we sort of, instead of taking the whole big picture, the whole curve, getting this big average velocity, we want just the very tiniest sliver right where point P is. We want to know what is the velocity here, and that's where we take the limit as time approaches 0, or the change in time approaches 0. That just means we're taking smaller and smaller and smaller and smaller sections of time. If you remember from calculus, this, let me actually fill it out. This is a derivative of x in terms of t. So when we take a smaller and smaller and smaller slice of something until it's almost infinitesimally small, right here at point P, that's where we can find this new speed, this new slope. Let me, so that will be the slope right when it touches at point P. That's the tangent at point P. So this slope right here, write it out, slope tangent at P equals the velocity at point P. So that is the value of an instantaneous velocity. To go back to my point about being a derivative, I can rewrite this equation above. V sub x as a function of time is equal to, I keep pressing that button. Okay. V sub x function of time is equal to the limit as t approaches 0, x over delta t. See, we're getting this smaller and smaller slice. This is formally written as dx over dt. These just very tiny slivers right here. And if we actually do this, we can get the slope at point P. And we know that the slope right here is the velocity at this specific instant. Okay, so let's move on to a little example with this. So we're going to look at example. And this is an example in the book. Most of my examples are in the book. So if you have a question or you need just a bit more clarification, you can look in there. I tried copying the graph that's in the book. This one is pretty good. But I changed the values slightly to match my own graph. So we have this position versus time graph. The position of a particle as a function of time is given by the curve shown below. We want to find the instantaneous velocity at 2 seconds. When is the velocity the greatest? When is it 0? Is it ever negative? So I'm going to try to keep the values in the graph in the page like this. Okay. Actually, what if I go like that? That helps just a bit. Okay. So what we know is that the instantaneous velocity, let me write it right here. Velocity is written as v sub x. And we know that this is equal to the slope of a line on a position versus time graph. So this is equal to the slope. And how do we find the slope of something on a graph? That is just rise over run. So how much does the line rise in the in the y direction? So how much does it rise? That is going to be the unit for x position right here. So x final minus x initial. And how much rise over run? So how much does it run? How much does it move to the right or left? That is the time final minus t initial. All right. So I don't think I have to go step by step with this. I'm just going to go. Well, I'll fill it in right here. So do a medium step by step. So we'll go. First, I need to find what I'm looking at. So I want to know the instantaneous velocity right at time 2. So right here is this point right there. And to save time earlier, I made a graph that looks nice, so I wouldn't have to rush. We have this dotted line. Let me get rid of this real quick. So we can see that right at time 2, it is tangent to the curve. It's tangent. It's very exactly parallel right at points time equals 2. Okay, and then I've just extended it outward in both directions and made some other dotted lines to be helpful. So here we go. So the final position is, we'll say we'll go up here all the way to 6. So we'll say that's 6 meters. And the initial position, we'll say we'll start here at 3 meters. And since we're going from here to here, we want to also get the time it takes to go from here to here. So final time, 6 seconds minus initial time is 2 seconds. This turns out to be 3 meters over 4 seconds. Or I could just say 0.75 meters per second. All right. That is our instantaneous velocity. So the velocity right at time equals 2. What were some other parts to this question? When is the velocity the greatest? So we've seen that the velocity is connected to the slope of the line. So what we're looking at, what we are looking for is, where is the slope the greatest or the most steep? So steep, like well, I guess there are 2 areas that there is a very steep slope. So let's go like this. I'll say the velocity is greatest where the slope is the steepest. So I'm going to zoom in a bit so I could actually write clearly. The velocity is the greatest where the slope is the steepest. Okay, so there are 3, actually, yeah, there are 3 areas I'm thinking of. So maybe around here, maybe around here, and we can also consider the other side over here. Now, I just said velocity is the greatest. I didn't say a specific direction. So this is a bit of a vague question. That's why I'm considering this last part. If the question was when is the velocity the greatest in the positive direction, then I could just keep it as just these 2. But for now, I think I'm going to consider that third part. So this is just a, estimation answer. I'm going to say the time around, so approximately, t is approximately, I'd say 1.5 seconds. T, approximately around 6. Approximately around 6 seconds. And t approximately around 8.5 seconds. And that's good enough for my little example. When is the velocity the greatest? When is the velocity 0? So zero velocity means a 0 slope. That is just a flat horizontal line. So where on this graph is there a slope of 0? Okay. In this case, there are 2 instances. So there's one right here, and there's one right here. So think of, let me back up a minute. See this curved line, see this tangent dotted line. So imagine following that along the path of this solid black line. And whenever that blue dotted line becomes completely horizontal, we can see it will be horizontal right here, and it will be horizontal right here. So those 2 places, it will be 0. They'll have a 0 slope, so we'll have 0 velocity. The 0 around t is approximately, minus minus 0.5, and t approximately around, I don't know, 7.5, 7.5. Okay, and the last tidbit, is it ever negative? And we can see that this just means a negative slope. There's a bit right here and a bit right here. So I'll just say negative. And we'll just summarize. T is approximately -1. T approximately around 8. All right. Now that we've done this example of a position versus time graph, we've seen that the slope on a position versus time graph is the velocity. What if we had a velocity versus time graph? That's where we're going to need to get into acceleration. We need to understand what that is first. So we will go like this. All right, moving on to acceleration. This is a term that can be misused. Acceleration is not the same as velocity. Acceleration is the rate of change of velocity. Here we go. It's the rate of change of velocity. So when you're in your car and you step on the gas pedal, you go from a velocity of, if you're at a stoplight and then you start going, you go from a velocity of 0 to maybe you go up to the speed limit. So there is a brief moment where you are changing your velocity. Then as soon as you're at the speed limit, then you're at a constant speed or a constant velocity. So this changing of velocity is acceleration. So A first we'll start out with a average, just the x direction. And this is all going to be very familiar since we've just gone over averages for velocity. This is v sub x, delta v sub x over delta t. So what is the change in velocity and how long did it take to do it? So this ratio is, it describes acceleration. You write this out in full as v final x minus v initial x over t final minus t initial. And this whole thing is a bit familiar. I'll just say, to save room, I'll say which also shows just like before, if I take this first bit and I multiply the delta t over, I can get a term for velocity. So this also shows the change in velocity is equal to the acceleration, average acceleration, times the change in time. Okay, so just like before, yeah, averages can be helpful some instances. Some instances, maybe we want to be more specific. Maybe we want to know the acceleration at a given time. This is where we need to know instantaneous acceleration. And this is also just like we've done before. So this is now a sub x. This is the limits as t approaches 0. We're just taking a very infinitely small slice. So limits as delta t approaches 0 of Vx over delta t. And I can explain this as the slope of a line tangent to a velocity versus time curve. Slope of the line okay. So we have, these useful tools that we can actually begin doing a vast majority of kinematics. Just knowing something's position, velocity, acceleration. Those are all of, almost all of the questions will revolve around finding one of these things. We want to know how things move. We want to be able to predict how they'll move. So from this point on, we're just going to elaborate on these three, concepts and maybe arrive at some more equations that can determine more things for us with these three concepts. But for right now, in general, like this, in general, I'm not going to do another big acceleration example, but I will sort of do a summary of the two kinds of graphs. So I have these two right here, and I've broken them into sections. What is different about these two? Well, one of them, the top one, is a position versus time graph. That's the first thing. Let's try to write this as clear as possible because it's going to be a lot of writing in here. So this is a position versus time graph. And we know that the slope on a position versus time graph equals velocity. Okay. The one on the bottom is a velocity versus time graph. And we know the slope here is the acceleration. I might have to move that second one down a bit, but we'll get there when we get there. So let's look at just the top example now. I'm gonna make okay. So let's look at each section. So for section 1, on this position versus time graph, we can see that the position is changing over time. So this shows that an object is, I'll say, moving. I'll say equals. Moving at a constant positive velocity. Okay, same thing for the yeah, I'll go down here to the bottom graph. Section 1 down here shows that we're moving with a constant positive acceleration. We have to remember that this is still a graph marking, one of the axes is itself some movement. So I need to also label what the velocity is doing. So this is a positive acceleration with a positive velocity. So I'll say in parentheses, it's steadily, I'll just say getting faster. Yeah, okay. 2, moving at a larger constant velocity for the top one. A large constant velocity. Constant positive velocity, I should specify. I'm going to have to move that down in a bit. Okay, so this next one. Actually, I'm just going to say larger to save some time and some space. So positive acceleration. And a positive velocity. Step in section 3 up here, see that it's not moving at all, but it is some distance away from where it started. So stationary at a distant point. Okay. For a section 3 down on the bottom graph, it is a flat line, but we remember that this is a velocity versus time graph. So it is remaining for a period of time from here to here. It is remaining at a constant velocity. It's not changing its velocity anymore. So constant constant positive velocity. Here's where I'm going to have to change things. So let me go right about there. So in fact, I'll move this one up too. So for section 4, the top one, this is where the object starts moving closer to the origin. So I'll just say moving. It has a negative slope now, so it's moving with a negative velocity. And for section 4 over here, this is the actual tricky one, because it is now changing its speed again. It is the slope of this is acceleration. It has a negative acceleration. So moving with a negative, it's at the very bottom, negative acceleration. However, we still have to remember that this is a positive velocity. So it's on the positive side. You see up here. So still on the positive side of the axis. So say with a positive velocity. And since these two signs are opposing, that means that this object is slowing down. Typically, whenever these two signs are opposing, that is called decelerating or deceleration. So I could put slowing down. Slowing down. And, you know, there's a lot of awful handwriting at the bottom. I will fix in a little bit. But this is where I want to stop for today. So when things are moving on a position versus time graph, the slope is velocity. When things are moving on a velocity versus time graph, the slope is the acceleration. And the last point I wanted to make was that when the signs on acceleration and velocity are opposite, that means there is a deceleration. So we see that the speed or the velocity is reduced. And when the two signs are the same, as with the other examples, see right here, positive and positive, that is when the object increases in velocity. Side note is these could have been both negative. So a negative velocity and a negative acceleration that will just make the object move more quickly in the negative direction. So whenever they're, so I think that's good for today. Up next time we will go more over acceleration, and I will bring up some kinematic equations that will be helpful for a lot of projectile and a lot of the problems on our homework, actually. So I'll see you guys next time. If you have any questions, you could stick around and ask. But otherwise, I can see you guys later.